So we're in section 4.3 now. This is actually the fourth problem in the homework, and it's the first sort of difficult problem that you'll encounter in this section, so I picked this as our initial problem to go over. So let me turn my pen on here. First of all, we want to find the zeros, or x-intercepts. And remember that essentially a zero or an x-intercept corresponds to a factor. So for example, if a function, I'll just kind of draw a generic function here, if a function happens to have an x-intercept at like x equals 2, then we know that x minus 2 is a factor. Okay, in other words, whatever number is an x-intercept, x minus that number becomes a factor. Okay, if the number was a negative number, like let's say negative 3, let's say the function had another intercept there, then the corresponding factor would be x minus negative 3, which is the same as x plus 3 as a factor. Okay, so x take away the x-intercept number gives you a factor. Okay, that's called the correspondence between factors and x-intercepts, which is very important. Okay, so essentially when we're trying to find x-intercepts, we're essentially also trying to find factors. If we find the factors, we know the x-intercepts. If I know x take away 2 is a factor, I know 2 is a x-intercept. If I know x plus 3 is a factor, then I know x take away negative 3, or negative 3 itself is an x-intercept of the function. Okay, so to find zeros, or x-intercepts, we know x-intercepts have a correspondence with factors. Okay, so if let's say x equals a is an x-intercept, then x take away a would be a factor, or a is just some particular number, like the 2 or the negative 3, etc. Okay, so that's kind of the idea here. Now, let me go ahead and clear some space. Okay, and so what we want to do is we want to use some tools. First tool is in the, talks about it in the online text, that if you take the factors of what's called the constant term. My constant term has lots of different factors. What goes into 100? Well, 100 does, right? Negative 100. Okay, so 100 and negative 100. What else divides into 100? How about 50? Negative 50. Okay, how about, let's say, 25? And negative 25. How about, let's say, 10? And negative 10. How about 5? Negative 5. How about 4? Negative 4. How about 2? Kind of running out of room here. 2, negative 2. Whoops, running out of room. And then, of course, 1 and negative 1. I'm kind of running out of room there, but 1 and negative 1. What are the factors of the coefficient, the leading coefficient? My leading coefficient here is 1. It's the coefficient of the highest power term. My leading coefficient here is 1. Okay, what are the factors of 1? Factors of 1 are just plus 1 and minus 1. So it turns out that if you look at all the ratios of the factors of the constant term divided by the factors of the leading coefficient, those are the possible x-intercepts of the function. Okay, so for instance, I could have like 100 over 1 because the 100 is a constant term factor, the 1 is a leading coefficient factor. So basically we want the constant factors of the constant term, divided by factors of the leading coefficient, all right, LC factors, leading coefficient factors. So 100 over 1, or 100 over negative 1, how about like 50 over 1, or 50 over negative 1, we could do 25 over 1, 10 over 1, 5 over 1, 4 over 1, 2 over 1, 1 over 1. So these are all possible, and then we could also do the negatives. Now, how do I know which of these is going to work? Well, a fast way to do it is put the function into your graphing calculator. Now, what if you don't have a graphing calculator? Well, you're going to need one if you're going to go further in math. TI-84 is the standard one that we use in just about all courses. You can temporarily download a TI-84 emulator on your phone. There's an app for it. Practice with it. But then on the actual test, you'd have to go to a testing center and borrow a physical, actual TI-84 because they will not let you have a cell phone with you because you could look up stuff on the net. Okay, but you can use the app to get used to the functions of the graphic calculator and then just use the actual one that you could check out from the testing center. Okay? Just contact your testing center, call them up, see if they have TI-84s to check out during testing sessions. Okay? But anyway, so here's what I would do. I'd go to y equals, and I have some stuff in there, so I'm going to clear it out. Okay, and go back up, and I'm going to put the function in. So I'm going to have x, here's your x button, and I have to go power 3. Now I have to get out of the power. Don't keep typing because you're up in the exponent right now. Let's get out of the power. X cubed plus 4x. Now for x squared, that's so common it has its own button. You don't have to use the caret. The caret or wedge is only really needed if you have powers different than 2. For power 2, it already has a power 2 button. Okay, let's see, plus 25x plus 100. So there's my function, okay? Now, what I'm now going to do is I'm going to basically plug these numbers in real fast. And the way to do that is with a table is probably the easiest way to go. So what I'm going to do is I'm first going to set up my table. That's the table set function. So second function, table set. And what I want to do is I want to be able to type in my x's. I don't want the calculator to pick them for me. The x's are the inputs or independent variable. And so I want to go down and make my independent variable go to ask so that I can type them in. And now I'm going to ask for a table. And it's going to tell me, okay, type in your x's. So I'll type in 100. And I'm looking to see if I get a 0. Okay, this is what this number is 1.04. E6 means there was no room, it was a big number, and you have to move the decimal 6 places over. Okay, so it's 1040000, some huge number. So that's not 0. Okay, let's try 50. 50 is one of my options. Not 0. How about 25? Not 0. How about 10? Not 0. How about 4? Not 0. How about 2? Not 0. How about 1? Not 0. Ruh-roh, right? I'm quoting a famous TV character, right? Scooby-Doo, one of our most famous actors. Okay, let's try the negatives. Now, when you do negative, you have to be careful. Don't use the subtraction button. This is the subtraction operation. This is the negative symbol for a negative quantity. They're different on the calculator. Okay, so I'm going to try -1. Okay, I got the sounds turned on my calculator. That's why you heard that noise. Okay, -2. I'm just kidding. Well, maybe I'm not. Okay, how about -4? Let's try -4. Ding, 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 ding. Did you hear a bell? Ding, 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 ding. What's the bell say? We have ourselves an x-intercept, -4, because it made the answer 0, made the height 0. So I already know that x equals -4 is an x-intercept. Now, that means that x take away -4 is a factor. And of course, we can rewrite that factor as x plus 4. Okay, so I already know that. Now, is there another way to do this? If you don't like this sort of methodology where you plug everything in, another way to do this, if you want, is if it turns out that the x-intercept is a whole number, a fast way to get this is if you go to table set and you keep your table on automatic and make your table start at 0 and make your delta table. The delta table is how much you change the x's by from row to row. Make that 1, so you're plugging in whole numbers. And now just generate your table. You can scroll up and down in your table and look for x values that give you a 0. Okay, and notice we see it right there. At x equals -4, we see a 0. So this method, where we just kind of automatically generate the table instead of plugging in all our candidates, will only work if it turns out that there's a whole number x-intercept. If it's a fractional x-intercept, it won't work. Okay, but this method will. Okay, where we divide the factors of the constant term divided by the factors of the leading coefficient. Okay, the so-called rational zeros theorem. Now, anyway, so what do we do now? Well, we celebrate. No, what we do is I have to now take this factor and remove it from the polynomial to see what's left. And the way we remove a factor from a polynomial is we do a division. Okay, so let me erase everything. Okay, and start again. What I'm going to do now is we know x equals -4. was an x-intercept, right? So that tells me that x take away -4 was a factor, which is another way of saying x plus 4 is a factor. Okay? That's supposed to say factor right there. Sorry about that. Okay, so I'm going to remove that from the rest of the polynomial, and we do that with long division. You can also use synthetic division. I kind of like to do long division because synthetic division only works in the case where you have like an x plus a number or an x minus a number, very special cases. Long division works in all scenarios. I'm kind of a long division person. If you like synthetic, you can do them in these cases, but just remember that only works for x plus a number or x minus a number. If you're dividing in some multiple of x or some higher power, you cannot do synthetic division. Okay, so this is my division. I want to remove the x plus 4 from the polynomial to see what's left over. The way you do long division is you say to yourself, okay, self, how do I make the leading term on the outside become equal to the leading term on the inside? What do I multiply x by to make an x cubed? And the answer is I multiply by what? X squared. X squared times x would give me x cubed. So now I'm going to multiply back down. X squared times x gives me x cubed. X squared times 4 gives me 4x squared. I'm going to stack that up right under the other x squareds. Now, this has been accounted for already. The x cubed plus 4x squared has been accounted for, so I have to subtract it to get rid of it. Okay? Let's go to a new color here, I guess. We'll try purple. Okay, so x cubed, take away x cubed is gone. 4x squared, take away 4x squared is gone. So I'm left with 25x plus 100, because 25x take away no x's is still 25x. 100 take away no numbers is still 100. Then you say to yourself, self, how do I make the first term or leading term on the outside look like the leading term that's on my new inside? And the answer is I just multiply by 25, right? 25 times x would give me the 25x. 25 times 4 is 100. I'm going to subtract all of that because it's been accounted for, and I'm left with what? I'm left with needing a drink. 25x take away 25x is 0. 100 take away 100 is 0, so I end up with 0. When the remainder is 0, that's important. If the remainder was not 0, that means that we either didn't divide correctly or this was not truly a factor. In order to truly be a factor, it has to divide evenly with no remainder. Okay? So what does this tell us? It tells us that my original polynomial, which is up here, this p of x, can be written as x plus 4 times x squared plus 25. Okay, so I've taken a third degree polynomial and broken it down into degree 1 times degree 2. Now, it's still not fully factored, though, because I still have powers. When you have powers, you're not fully factored. So let's keep factoring. Okay, how would I factor this remaining? I'm going to rewrite it up here because I'm running out of space. So I've got x plus 4 times x squared plus 25. Now, how do I factor x squared plus 25? I can try doing it by hand, xx, and if I try plus 5, it's going to give me a plus 10x in the middle, which I don't have here. If I try a minus 5, it'll give me a minus 10x, which I don't have, which means I can't really do this by hand. When you can't factor a quadratic by hand, you either use quadratic formula, or if you get lucky and the quadratic, this is a quadratic factor, meaning degree 2 factor. It's a quadratic factor. When you have a quadratic factor that happens to not have any x's in it, we can do a shortcut. We can just set the quadratic factor equal to 0, because remember, finding an x-intercept, finding where the factor is 0, will tell us the remaining factors. Okay, because if you have a 0 or x-intercept, x minus that number will be a factor. So finding factors and finding x-intercepts, basically the same process. Now, how would I solve this? Since there's no x's, we can use what's called the square root property. I can just move the 25 across. So I got lucky here, I don't have any x's. If I had some x's, this would be a lot harder. I'd have to use quadratic formula. Okay, so I'm going to have x squared equals negative 25. Take the square root of both sides. square root x squared equals plus or minus, remember when you take the square root of something squared, you have to put plus minus on the other side, root negative 25. Okay, so that means x is plus or minus. Now, how do you do root of negative 25? I'll kind of remind you up here. Root of, I guess I'm kind of running out of space. Root of minus 25 is the same as, when you have the square root of a negative, just write it as square root of negative 1 times the positive of that number. And then break it up into two roots, root negative 1, root 25. The root of negative 1 is I, and the root of 25 is 5, so 5i. Okay, so if plus 5i and minus 5i are your zeros, in other words, these make the function become 0, that means x minus them are factors. So that means I can rewrite my polynomial as x plus 4 times, instead of x squared plus 25, I can write that part as x take away 5i, and then x take away negative 5i. X take away positive 5i, I just wrote that. X take away negative 5i is the same as x plus 5i. Okay, so this would be the full factorization. How do I know I'm fully factored? Because there's no powers left. Okay, notice I get two what are called complex factors and one real number factor. Okay, so those are my factors. What about the x-intercepts? Okay, in fact, in this case, okay, so they want the zeros first. So up here, this is here they want the factors. So my answer here would be this. But they also, up here, they wanted the x-intercepts. Remember, the x-intercepts are going to be wherever each factor is 0. So to find the x-intercepts, what I would do here is I would say, okay, x plus 4 is 0 where? At x equals negative 4, right? So negative 4 is one of my zeros. X minus 5i is, well, actually, you have them right here. These are your zeros. We converted those zeros into factors, right? I converted the plus 5i and the minus 5i into the factors. X take away the 5i and x take away the negative 5i, which is the x plus 5i. So I know 5i and negative 5i are my additional zeros. Okay? A zero is a quantity that makes the function become 0. Now, if the 0 happens to be a real number, like the negative 4, it's also an x-intercept. These won't be x-intercepts because you don't see them on the graph because they're complex numbers, but they do work. They will make the function become 0 if you plug them in and work it out. Okay? So again, use the rational zeros theorem to look for candidate zeros and check them by using where you put the table to if you go to table set, put it on ask, and you can type in your choices. Or put it on auto and hope that your 0 is a whole number, because then when you look at the table, you'll see a bunch of whole numbers being plugged in, and hopefully one of them makes the function 0. Okay, so we got lucky there. All right, that was fun, huh? Yeah, I just checked it, yep. All right, so let's go to the next one. Okay, so here we are on problem 5. In this case, they've already done the factoring for us, which is really nice. Okay, we don't have to factor things ourselves. In the last problem we did. So in this case, they just want to know what the zeros are and then the horizontal intercepts. So remember, if x minus 2 is a factor, then wherever x minus 2 is 0, that's going to be an x-intercept. So that would be at x equals 2. Same thing here. Right, same thing here. Whenever a factor becomes 0, you get an x-intercept. So I've got these 3 x-intercepts. Okay. So in this case, for these zeros or x-intercepts, they just want you to list those. They don't want xy coordinates. So I'm just going to list them. I'll put them in from smallest to largest. So negative 11 is my smallest. Then I'll go to the 2, then I'll go to the 4. It's usually good to go kind of in what's called ascending order from small to large. Now, an intercept is sort of an xy point. So for the negative 11, the x is negative 11, the y is 0 because this is an x-intercept. Same thing here. Okay? We just want you to make these into points just to remind yourself of the difference between sort of, the 0 is a certain x location, but the actual intercept itself is a point, an xy pair. Now what about the vertical intercept? How do you get the vertical intercept? That means the y-intercept. For the y-intercept, you make what 0? You make x equal to 0 and plug that in. So I'm just going to do f of 0. Right? F of 0 is what? 4 times 0 take away 2 squared. 0 plus 11. 0 minus 4. So that's going to be 4 times 11 times negative 4. And if I worked it out, you get negative 704. Whoops. Okay, so my vertical intercept will be the point 0 for x, negative 704 for y in this case. All right, so this was not too bad. Maybe just one bad, not too bad. Yeah, just one bad. There you go. All right, so let's go on.